Hello students, let's study Kepler's second law, the law of the areas. The statement of the law is that the radius vector connecting the sun and the planet sweeps equal areas at equal times. If you have the planet in its elliptical orbit, this area here on the right-hand side is equal to the area on the left-hand side if the planet is spending equal amount of times from this point on the orbit to this point of the orbit as it passes from this point of the orbit to this point of the orbit. So closer to the sun, the planet is going faster, and further away from the sun, the planet is going slower. Now, this is how this law is traditionally taught, almost like a curiosity. This is how it got passed to me in popular astronomy books that I read as a child, and again in high school physics. In college, we walked the extra mile of proving from Newton's laws that Kepler's second simply reflects angular momentum conservation. This is usually done by climbing down the pedestal of differential and integral calculus to the pedestrian world of Euclidean geometry and defining the strange concept of area velocity, which is then proved to be constant. I want to show you that Kepler's second law is way more profound than that. It's a truly revolutionary law. In fact, it has to do with finding the planet in the orbit. Suppose that you have a practical problem, just to find the opposition of Mars. When is the next opposition of Mars going to happen? And where in the sky are you going to find Mars when it's in opposition? So these are the orbits of the Earth and Mars. And as you see, Mars' orbit is very elliptical and is going slower closer to the sun and faster further out. Kepler's first law only gives you the shape of the orbit. It says nothing about how to find the planet in its orbit. If you want to know where exactly the planet is in the orbit, you have to consider that the true anomaly is a function of time. So from Kepler's first law, you have how to find the true anomaly as a function of the eccentric anomaly. Both of these, the eccentric anomaly and true anomaly, are nonlinear functions of time. So how to find them? This is the fundamental question that Kepler's second law tackles. And the answer to that is the mean anomaly is the eccentric anomaly minus the eccentricity times the sine of the eccentric anomaly. The mean anomaly is a linear function of time. If you measure the time, you have the mean anomaly. And then you apply this to find the eccentric anomaly. And then you plug this onto this equation to find from the eccentric anomaly the true anomaly. And that's where the position of the planet is. What is important in Kepler's second law is this equation. This equation here states that on the left-hand side you have time, and on the right-hand side you have area. We're getting ahead of ourselves. Let's find out exactly what I mean by this. But the main point that I want to make here is that what is important in Kepler's second law, it's not the area, it's the time. It's by the time that you find the planet. It's a question that one rarely asks oneself when studying Kepler's second law. Why did Kepler care about area? The point is Kepler wasn't really caring about area, he was caring about the time. So let's see how exactly he found this mathematical statement to relate areas and time. So to understand why Kepler needed a new law, let's look at what existed before him. Let's assume that both Earth and Mars go in circular orbits, centered at the sun, in uniform motion. At any instant of time, the position of Mars is given by x being equal to the semi-major axis a times the cosine of this angle m, and y is equal to a times the sine of this angle m. Now, m is called the mean anomaly, and it is equal to omega times t, where omega is the orbital frequency and t is the time. Now, the orbital frequency is 2 pi over the orbital period, call it big T. Now, notice that everything but time in the definition of mean anomaly is constant. Mean anomaly equals time. Mean anomaly is time. This is very important for understanding Kepler's second law, because Kepler's second law is about finding the mean anomaly. So let's see how this model fares against the observations. This figure here in the upper left, what you're seeing is the longitude versus time for Mars in red, and for Mars, if the orbit was a circle, that's in magenta. It follows more or less, but then once Mars is retrogradating, it doesn't fit. On the upper plot here, you're showing the variation between the true longitude and the calculated longitude with the circular model. As you see, it's as far as 30 degrees. So this model is obviously very wrong. The lower left plot is showing here the orbit of the Earth in blue, the true orbit of Mars, which is in red, and the circular model that we are considering in magenta. And this is the heliocentric view, and this is if you change the reference frame to Earth, the geocentrical view. So Mars orbital path seen from Earth is the red, and as you see here, the circular model gives you very wrong predictions. The model does not reproduce either the shape of the orbit or the longitudes. The predicted positions of the retrogradations, specifically, as you see here from the upper right plot, are off by as much as 30 degrees from the actual position of Mars. There is absolutely no way that you can use this model to predict the position of Mars.